Good day. In this video lesson, we will be discussing about situational problems involving conic sections. So this is our final discussion for conics, and therefore, you will be applying all your learnings here in this topic. Now, first things first, let's recall what are the four conic sections. We have circle, parabola, we also have ellipse, and then hyperbola. So please recall their definitions and take note of the distinct properties as well as the equations of each conic sections because we will be using it later on when we are already solving the word problems. Before we jump into the discussion, let's have first this math beat. What do you think is the reason why Greek mathematician Pythagoras is being managed to come down by his colleagues in sciences, Stephen Hawking and Neil deGrasse Tyson, before the COVID-19 sign? Do you think that the proposal for social distancing is correct? If not, what do you think is wrong in the poster? As you can see in the sign, 4 people are equidistant 6 feet each in the plane. The error of this representation can be easily recognized by drawing a right triangle as in the next figure. We have in it that the two legs has equal lengths of 6 feet. Tables on the sign also show that the hypotenuse or the diagonal line from one corner to another is also 6 feet long. But it is not a right triangle, rather an equilateral triangle if all the 3 sides are equal. So it violates the Pythagorean theorem. So now, what do you think will happen if people start seeing this advisory and do not figure out what's wrong? Okay, then the coronavirus is going to keep spreading. What do you think is the appropriate geometric figure that represents the social distancing? If you said circle, then you are right. Now we all know that circles are commonly encountered in our daily lives. In your name view, can you also recall from our first discussion in Precalculus about some situations or real-life applications involving the remaining conic sections? So at the end of the lesson, you're expected to solve situational problems involving conic sections. Now let's start with the first conic section, which is a circle, by solving this problem related to the scenario in the previous meme, which is about social distancing. Suppose the IATF trace infected persons labeled C, O, B, I, and D to be located at negative 11, 12, 14, negative 4, negative 5, 13, 3, and 18, negative 5, respectively. The map with 1 unit is equal to 1 feet. Determine whether each of the persons S, A, F, and D, located at negative 19, 19, negative 19, negative 19, 0, 19, and 19, 0, respectively, is safe from catching coronavirus to these infected persons. You will notice that this problem requires you to apply your knowledge about the graph of a circle. So throughout the lesson, I have assumed that you already mastered plotting points and are familiar with sketching the graph from our previous discussions. Now that you have encountered all equations and graphing, now apply it in solving situational problems involving conic sections. So going back to the problem, we first plot the location points of those infected with COVID-19 on the Cartesian plane, labeled as C, O, B, I, and D, together with the persons S, A, F, and E, before graphing the social distancing circles of each infected person. So in this video, let's say we have already plotted the given points in the problem. Now, if you will make use of a graphing calculator, you need to get the equation of the social distancing circles of persons C, E, I, and D co-located at the centers, which all have a fixed radius of 6 units on the xy plane, to sketch its graph. From the standard form of the equation of a circle, x minus h squared plus y minus k squared. First, for person C at negative 11, 12. So this is now the center of the corresponding circle. So these are the coordinates hk. So therefore, equation is plus 11 squared as y minus 12 squared is equals to. So since all the circles have a fixed radius of 6 feet, we'll equate all our equations to squared. So equated to 36. Next, for person O at 2, we have x minus squared plus y minus 14. For person B at negative 4, negative 5, we have x plus squared plus y plus 5 squared equals to 36. Then for I at 13, circles first before plotting the locations of persons S, A, F, and D to check it one by one if each of them is safe from COVID-19. Another method is to get the distances from each point and compare it to 6 feet, which is the radius of the social distancing circle. But this approach requires long solution. So imagine how many will get infected if no social distancing measures are in place. Okay, any individual who want to be 6 feet away from a person infected should position themselves somewhere on a circle that has the infected person at its center and the radius of 6 feet. By maintaining this of at least 6 feet away, restricting yourself within the locus, then this is enough to keep you safe from catching the infection from someone else. Here comes another conic problem related to the pandemic. A frontliner sprays disinfectant on a street to disinfect the area. He holds the hose 3 feet above the ground with the hoses opening as the vertex and the chemical liquid flow following a parabolic path. The liquid strikes the ground a horizontal distance of 2 feet from where the opening is located. If he were to hold the hose 3.5 feet above the ground, how much further would the liquid strike the ground? So whenever you are given word problems like this, you have to identify what kind of conic section is involved. So is it a circle, parabola, ellipse, or hyperbola? Sometimes it is explicitly mentioned, but there are times that you just have to find keywords for you to determine the type of conic section involved. So by looking at this word problem, so we can take this word parabolic. Okay, so that means we're dealing with parabolas. So that means we will be using the concept of parabola in answering this particular word problem. So after you identify the type of conic section, you have to illustrate. Okay, so when you are illustrating, it is helpful if you will put it in a Cartesian plane so that we can identify some things that we can use in order to solve. Okay, so again, we have a parabolic path of the liquid, and let's say we will put it in a Cartesian plane, so like this one. So this red curve here, this is the path of the disinfectant. So as you can see, it's in the shape of a parabola. You can place it wherever you want, but it's easier if you will place the conic referring to the origin. So using the origin as the reference point for the ground, thus 3 feet or 3 units above it is where we will place the opening of the hose or the parabola's vertex. So in this example, we place the vertex of the parabola where the path of the liquid starts at the positive axis. Positive since it is only the value or magnitude that is commonly asked in real-life applications. So in this case, we put the vertex on the positive y-axis, where x is equal to 0 at 0.03. Since the trajectory of the liquid is vertically downward from a height of 3 feet to the ground, or in this illustration, it flows towards the positive x-axis. Okay, so it's the point right here. So again, you can place the figure anywhere you want, but again, it's better or it's advisable if you will maximize the use of the origin. So this horizontal line right here, the x-axis, where y is equal to 0, corresponds to the ground. So it was mentioned in the problem that the liquid strikes the ground a horizontal distance of 2 feet from where the opening is located. So if the x-axis represents the ground in this illustration, and the vertex of the parabola represents the opening of the hose, then it follows that the parabola intersects the positive x-axis at 2 units. Or in simple words, it passes through the point 2, 0. So since we're given now 2 points, the vertex of the parabola at 0, 3, and another point on the parabola which is 2, 0, then we can derive now its equation using the standard form of the equation of a parabola leaning downward, which is x minus h squared equals to, since downward is negative 4c times y minus 8. And then all we have to do is substitute the vertex and the point to our equation to solve for the variable c, which is still unknown. Again, the vertex is at 0, 3. So these are the coordinates of hk. So h is equals to 0 and k is equals to 3. Also, we have another point 2, 0. So these are the coordinates x, y. So we have x is equals to 2. So 2 minus 0 squared equals to negative 4c, which is still unknown in our equation. Then y is equals to 0, so 0 minus 3. Simplifying and solving for the value of c, so we have c is equals to 2 squared all over negative 4 times negative 3 is 12. So this simplifies to 1/3. So let's substitute now the values that we know to derive the equation of the parabola. So now we have, since h is equals to 0, so x minus 0 is still x, so x squared equals to negative 4 times c, which is 1/3, so negative times 1/3 is negative 4/3 times y minus k, since k is equals to 3, therefore y minus 3. So this is now the equation of the parabola that represents the chemical liquid or the disinfectant. Now, the question is, if he were to hold the hose 3.5 feet above the ground, how much further would the liquid strike the ground? So we can draw again another parabola here, same curvature from the previous one, which represents again the path of the liquid flowing from the hose but in a different position, with vertex at 3.5 units above the x-axis. So at point 0, 3.5. Or we use again the same old parabola where vertex remains at 0, 3, but the line that represents the ground will be shifted to y is equals to negative 0.5. Since the liquid will now strike at 3.5 feet above the ground, so overall, this must be 3.5. So we just need an additional 0.5 here. And the initial height of 3 feet. So what's being asked here in the problem is the additional, or from the word further, the added distance that it will cover by increasing the height by 0.5 feet. So we need to consider this 0.5 here, where the liquid strikes the ground with y is equals to 90.5 and a known value of x. So therefore, this point here is x at 8.5. So from the equation of the parabola, this gives x equals to the square root of 94 thirds times 5 minus 3. So calculating for the value of x, we have x is equals to square root of 42 over 3. So we simply subtract it by 2 feet, the initial distance covered by the liquid as mentioned earlier, to find the remaining horizontal distance it needs to travel before striking the ground. So we subtract it by 2 feet So this must be in feet. For calculating, this is approximately equal to 0.61. So this is the horizontal distance the liquid will further travel to strike the ground. So that's the answer to our problem.